start this video by showing October, but really all you can see is her backside. So there you go. There's my cat. It's been a while since we've seen her. But we're going to go into indirect proofs, and I accidentally chose green, so it's a different color title, but we're just going to go with it. Or might I say, because it's green, let's just grow with it. Let's just grow with it, maybe. Okay, it's getting worse. What are indirect proofs? Indirect proofs are also known as proofs by contradiction. And that's how I always learn them. I had never really heard of indirect proofs. I always heard about them as proving things by contradiction. And that's what we're out to do. So direct proofs, by comparison, we're starting at our knowledge base and showing our conclusion. Indirect proofs are kind of the opposite. It's saying that we're going to assume our conclusion is false. And then we're going to show a contradiction. This is also called like reductio ad absurdum or something. I can't speak Latin, but it's something like that. Okay. So if we assume not our conclusion, then we're going to show that there's a problem somewhere else. And if we do good logic and say and our conclusion is that there's a problem somewhere, then theoretically, the only place that could be a problem is the assumption. So what is this going to look like? Let's go all the way back to this knowledge base. Okay. And actually, let's just take the knowledge base. Take this knowledge base. And what can we do with this if we do a proof by contradiction? One of our conclusions, let's start with our last conclusion, right? The last thing we said was that F was false. That was our conclusion. How can we prove this? Let's say we don't want to do a direct proof, but we want to show that F is false. The way that we're going to do that is that we're going to assume F is true. We're going to assume F is true and then show that this causes a big problem. And if that's true, our assumption must have been wrong. And if F is true is false, if saying F is true is a false statement, then F must be false. All right. So here we go. Well, and again, I challenge you to try to do this on your own. See if you can make those steps. You are really kind of working backwards from what we did in the last video, but it's really good practice to pause the video and challenge yourself to see if you can get it. All right. Well, if F is true, then what do we know? Well, that means this whole thing is true. It doesn't matter what E is. Right? F or something. Well, if F is true, this something is true. Well, if the premise of an implication is true, then the conclusion has to be true. So that means D is true. Well, and again, let's go over here. This has to be false. So this has to be false. Well, if this is false, the only way this can be false, if D is true, the only way this can be false is if C is false. A can't be true and C be false. If A is true, then C has to be true too. So C is false. That means A has to be false. All right. Well, if A is false, that means B has to be true. The only way that one of them is true is if, well, we know A can't be the one that's true, right? We know A is not the one doing the group work. So B's got to do it. All right. So that tells us that B is true. And then, uh-oh. Well, we also know that B is false. Uh-oh. Uh-oh. What's going on? Well, if every one of our logical links was correct, and they were, anyone else can check them. If all of our chain links of reasoning were correct, then the only place we could have made a mistake is right here. This is the only thing we assumed. Everything else was good logic. So this could not have been true. Because if this is true, we get some problems. And that's what proof by contradiction usually looks like. That's what indirect proofs look like. Why is it called proof by contradiction? Well, because we arrive at a contradiction. B can't both be true and false. All right. And this is usually how these are going to look like. They're also called indirect proofs, right? Because we're kind of working backwards a little bit. We're not even trying to prove that F is false necessarily, right? We're trying to say, well, what would happen if it were true? And a lot of things, this is an example, and I chose this example because you can do it both ways. But a lot of times it's really, really hard to show something is true by direct proof, but easy by a counterexample, or sorry, not by counterexample, by a contradiction. And so sometimes if you're trying to prove something, you don't know which way is the best way to prove it. Sometimes it can be helpful to say, well, what would it look like if it weren't true? Would we have a problem? Because that's one of the easiest ways to prove whether it's true or not. And then another reason why proof by contradiction is really nice is kind of just the way that counterexamples work. It's easier to prove that something's false than to prove something is true, right? For example, if I'm trying to say every day of the year is sunny. To prove that's false, all I need to do is find one day where it's not sunny. But to prove that every day of the year is sunny, I have to look at every single day and show that it's sunny. So a lot of times things are easier to prove, like to disprove than prove. So a proof by contradiction kind of lends itself kind of in that direction. Let's do a more mathematical proof. These proofs have all been with formal logic. What do more algebraic proofs look like? All right. And I'm not going to be having anyone do any super fancy mathematical proofs. You're not going to like prove the fundamental theorem of calculus. You're not going to prove like derivative laws. I don't even know if you've used derivatives. We're not doing that. But I do want to show you what a mathematical proof kind of looks like that's more algebraic. So let's do another one. And we're going to prove something pretty daunting, in my opinion, but the proof is pretty elegant. It's pretty nice. I want you to prove that the square root of 2 is irrational. So the square root of 2, if anyone, plugs it into a calculator, you're going to get 1.41 blah, 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 blah. I think it's about that. And it's going to go on forever. That's what irrational number means, basically, is that, it goes on forever without any pattern, really. Another way to think of irrational, a more precise way of thinking about irrational, is just not rational. All right, which sounds really stupid, honestly, when you write it like this. Of course, Jason, of course irrational means it's not rational. But what does a rational number mean? Rational means that it can be written as an integer divided by another integer. So like 2/3 is a rational number, right? 0.6 repeating is a rational number because it can be written as 2/3. These are examples of rational numbers, okay? Pi is another thing that's not a rational number. Euler's number E is another number that's not a rational number. A lot of square roots can be irrational unless they're really nice square roots, okay? So we're going to prove this by contradiction. What's the first step to prove something by contradiction? We're going to assume not B, and then we're going to just see, does anything bad happen? Does anything bad happen if square root of 2 is a rational number? Spoiler alert, something bad's going to happen. But hopefully not that bad, right? Hopefully we can still go to bed and sleep tonight. All right, so if we assume that the square root of 2 is rational, what happens? Well, if square root of 2 is rational, then we know that square root of 2, oops, circled the wrong thing, is going to look like this. All right, for some numbers A and B, square root of 2 is just A over B. And again, here A is going to be an integer, and B will also be an integer. And let's make an assumption, and a very easy assumption to make, right? If this fraction can be reduced, it will reduce into some other ratio of integers. So let's just say A over B can't be reduced. And we're definitely using a theorem here, right? We're using a theorem that's saying, well, if it can be reduced, then there's another set of integers that we could write it like this. Okay, so let's just choose ones that can't be reduced to make things a little easier. All right, a little more straightforward, give us more to work with. All right, so if that's the case, what happens? Anytime you have two numbers equal to each other, if you square both sides, the numbers are still equal. If you have two equal numbers and you square both sides, it's equal. So let's square both sides and see what happens. If this is true, then this must be true. And if we square both sides, that must be true as well. We square both sides, we get this. And we can find out that a squared is actually double of b squared. Right? If the ratio of a to b is square root of 2, then the ratio of a squared to b squared is just 2. That all makes sense. That seems pretty good. No problem so far. Everything's fine. Everything's fine so far. But what we're going to notice is that this means a is an even number. Sorry, a squared is even. And again, we're going to use another theorem of math that's proven that if a squared is even, well, think about every odd number. And again, we're using a theorem. I'm not asking you to assume this. We're using something that was proven somewhere else. But I just want you to trust me on this, give you some intuition. Think of if you square an odd number, it's always odd, right? Because an odd number means it's not divisible by 2. So if you square it, it's still not going to be divisible by 2. And similarly, if you square an even number, it's still going to be even. And in fact, any even square must have had an even square root, as long as it's an integer. And yeah, we knew a was an integer. So this also tells us that a is even too. And if a is even, what does that mean? What does an even number mean? Even number just means it's double some other integer. All right, so you can see this is pretty tricky. There's a lot of stuff going on here. I want you to try to follow as best you can. You don't need to be able to prove this yourself, but just stick with me to see what a proof by contradiction looks like. And again, this is a pretty gnarly proof to prove that square root of 2 is irrational, but we're actually almost done. Remember what we're doing. Proof by contradiction. Indirect proofs are just assuming the opposite of what we wanted to prove, and we're going to see if there's a problem. There's no problem so far. Okay? We know a must be even. So if a is even, it's double of some number. What does that become now? Well, if a is double some number, that means we can write this. This is no problem. A is the same thing as 2 times some number, so let's just replace it. And then we square things. We get 4c squared is equal to 2b squared. All right, we can divide both sides by 2, no problem. Right? If we divide both sides by 2, what do we get? We get something very interesting here. We get that b squared is also an even number. Uh-oh. Why is that a problem? Well, that means by the same logic we used up here, that b must be an even number as well. And why is this a problem? Why is it a problem if both a and b are even numbers? We said we're choosing a and b to be simplified. We're saying we can't reduce a and b. There's going to be an a and b that makes this work. Let's just reduce whatever numbers it would be. So we have a fully reduced form. But if two numbers are even, they're both divisible by 2. We are not reduced. So this says together that a over b is not reduced. Uh-oh. Warning, warning. Here, saying a over b can't be reduced. Here, I'm saying a over b can be reduced. We got a contradiction. Sometimes I've seen it written this way. Contradiction. This is a contradiction right here. We've blown up the universe by assuming that square root of 2 is a rational number. Well, now we're going to have to check. Was all of our logic correct? Were the theorems that we use proven, right? Those are all important things to check. And if those things all check out, the only other thing that can go wrong is our assumption. So thus, the square root of 2 must be irrational. It can't be rational. If it's rational, we get a contradiction. And if you want to be cool, you can write QED. Or if you want to be pretentious, QED is also good for that. No offense to anyone who uses QED. It's also something in Latin, and it basically says, I've shown you what I wanted to show you. Thus I have demonstrated. Quod eram demonstratum or something. I don't know. I don't know Latin. But that's what proofs by contradictions look like. Again, you don't need to be able to do this proof. I just want you to follow it and see the format, see the flow of what it looks like. Just like with our last example of just assuming the conclusion's not true and seeing what hell breaks loose. Okay? Let me know if you have any questions about this. And next up, we'll talk about proofs by induction. How can we prove things for every integer? And it's fun because, I'll spoil it a little bit, we just show it for one integer and then say, well, if it's true for an integer, is it always true for the next integer? And then if it's true for one and it's true for the next, then it's true for the next, then it's true for the next. And if it's always true for the next, then we got all of them. Well, in one direction anyway. Let me know if you have any questions and have a good rest of your day.